So today it's a talk about deep learning and trying to think about, in some sense, the unreasonable success of deep learning. As I will discuss, you should not be able to learn tasks that are highly dimensional, and deep learning manages to do that. So why is this the case? So let me thank collaborators over the years. Today I would like to talk about some work that's quite recent. Maybe it has been 2 months on the archive with those members of my group. So the question would be, what in the world, what in the data structure make them learnable? And I will be thinking about the hierarchical structure of data and how deep nets can try to learn them. And so this would really be physics, because it's very hard to do rigorous math on that. So we're trying to bring simple models and guesses. Theory is the best guess in physics. So guesses to compare observation with ideas. I hope it will motivate more rigorous works. Okay. So what is the question? So how do I change slide here?
The arrows.
The arrows. Okay, good. Okay, so think about, for example, just like Ricardo told, think about classification, supervised learning. Classical example, you want to learn cats and dogs, and maybe you have a bunch of images that are labeled, maybe 1 million images. What you're really trying to do is, from those known examples, build an algorithm that can tell you what happens for a new picture that you have never seen. The problem is that data like that, for example, images, live in very large dimensions. I mean, to specify an image, at least neighbor, you need to specify, each pixel and its color. And so the dimension of that is in the thousands. You have more educated estimation of dimension of data, but it's still very large. And the problem in high dimension, there is a geometrical problem. So these little crosses are pictures, and this plane here is a very high dimensional space of images. It's that in large dimension, even if you give me many data, so in this talk, the number of training data is P, and the dimension of space is D. The distance between neighbors in large dimensions, so delta, is almost not changing, because like P, the number of data to the power -1/t. So imagine D is 100, and this exponent is essentially 0. It means those guys don't get close to each other. So when you're given a new picture, it's far away from any picture in your data set. And you can show that if you assume little structure on the task, for example, you're trying to regress, functions at Lipschitz or something like this. The only way you can do well is by making delta become very small. So if you assume little structure, delta has to be small. The only way delta becomes small is to have a number of data which is itself exponential in the dimension. So think about exponential of 100. I mean, you will actually never make it. So we know that algorithms can make it. And okay, so Ricardo told us how those algorithms work. So remember, you put those data as input. F here will be the output, xi is the data, w are all the parameters. And then what you do is that you fit all those parameters, such that, for example, for every cat you have, if you think about binary classification, for every cat you have, this quantity is larger than m. So m is a margin related to the kappa in the previous talk. So you fit your parameters such that all the cats have an output larger than m, and all the dogs are smaller than -m. Okay, so you learn from examples. After you do that, you show a new picture. And when you show a new picture, the miracle is that the sign of f is actually indicative of being a cat or a dog. And you have all those amazing examples where you have, which are high dimensional. I mean, you can think about the game of Go, think about the number of configuration of Go playing. It's also cursed by dimensionality. And so we lack the principles to understand why it's working. And the fact that we don't really understand why this curse of dimensionality is beaten also means that we really have no clue a priori of how many data do we need to learn a given task. So, maybe for cats and dogs, you need 10^5, 10^6 data. But I told you, if you really assume no structure, it should be 10^100 or more. So we even don't really understand the order of magnitude of the data we need to learn a task. So there is an idea that I think is essentially correct as to why deep learning may work. And it has to do with the fact that actually all those questions, you can also ask them for brain. And here, it's an aspect of deep learning which is also similar to what our brain is doing, is a notion that after you train a deep net like this, actually neurons have learned an interesting representation of the data. And what you find is that, for example, if you are training on image data set, that maybe the first layers, they learn how to react to low features of the data, like having an edge somewhere. But if you go deeper, then neurons starts to respond to more and more abstract aspect of the data, like, you know, the face of a man or the face of a cat. So what questions are, when are deep learning actually building an interesting representation or not? So we'll be discussing that. So that would be, we'll see that there are different regimes. Sometimes you do, sometimes you don't. So we can compare the benefits of building such a representation. And the intuition is that it's useful to do that because essentially, if you manage to build this kind of representation, maybe you really lower the dimension of the problem. You started with a problem that's highly dimensional, but maybe this kind of representation have many invariants and they are much lower dimension. So in this presentation, I want to talk about invariance of this representation with respect to discrete changes. So maybe if you are looking left or looking right, this neuron would still fire, or if the mouth of the man was open or not. And the question we want to think about is, how many data do you need to build representations that start to acquire such invariances? It's a very difficult question. I will try to think about it in very simple models, that even those simple models, we can't solve them exactly at all. Okay, so I have a few slides that I think are useful also to place this work in the context of other talks in this session. So thinking about overparameterization, landscape, loss landscape, when you fit your data, but also training regimes that will be discussed this afternoon. So you have many benchmark data sets, and we look also at CIFAR, like image of plane, dogs, and so on. Here, those data are, even for a simpler data set, MNITs, you know, those digits. And it's useful to think about a phase diagram. So in this slide, I'm not going to tell you what's in it, but just the axis. So the two axes that will be important are the number of parameters. And so here, what we will do, we look at a deep net, fully connected, or CNN. I will come back to CNN later. And we just change the number of neurons per layer. Okay, we increase the width of the network. We're not playing with the depth, it's fixed. So this is n, the number of parameters. And another parameter that actually turns out to be important is the margin. So actually that was also discussed in the previous talk, the margin. So how much, when you want to fit the data, how demanding are you? You know, I told you the output has to be larger than m or minus m, depending on the layer. And it turned out that, so this is not the number of parameters, and this axis is the inverse margin. So actually here you have a very small margin, and here you have a very large margin. For the specialist, it's completely equivalent to think about the margin being fixed and changing the initialization of the weights. So this would be large initialization of the weights and small initialization of the weights. So, okay, so that's how should we parameterize, how many parameters do we need to actually fit the data? And that's directly connected to the previous talk we have. So here, I'm just going to ask you to look at the color on this phase diagram. And so essentially, what you do, you randomly initialize your weights, and then you bring your loss. You want to fit your data, you have this loss function. You bring it you try to minimize it. In the white region, you manage to hit bottom, and the loss is 0. And in the dark region, you don't. And you have a phase transition. Actually, here it's line here. A line of critical point, if you want, that separates a region where actually the landscape is glassy and you cannot fit the data, from a region where actually you can hit bottom, and then you have many, it's a continuous setting, the weights we do gradient descent, so we have continuous weight, so you can move along valleys that are completely flat. Okay, so there are interesting discussions. This phase transition is a jamming transition, as was already discussed before, and there are interesting questions of which universality you are, and so on. But for this talk, it just means that, you know, if you crank up the number of parameters, you will be able to fit your data. You don't need to worry about being stuck. Then what you need to worry about is overfitting. And as you were also told in the previous talk, there is magic in deep learning because, I mean, Fermi told us with 5 parameters they can fit an elephant, but with deep learning, I mean, you take billions of parameters and you only have millions of data. So Fermi was wrong on that one. And so in this phase diagram, now I'm going to ask you to look at the Z, the altitude. And what you see, so that's the blue curve here, what you see is a test error. So after you train, what is the probability that you do a mistake on a new data? So you would like this to be as small as possible. And so one would expect that this should be a sort of parabola. When the number of parameters is large enough, you do really poorly. But it's not like that. In fact, it has a shape that has then been called double descent. So initially it makes sense, you need to increase the number of parameters because you don't fit your data well. When you just start to fit your data close to this transition, it's locally worse. And then, amazing part, you have this second descent. It means you crank up the number of parameters in a region where you already fit perfectly your data anyway, and it's good to increase the number of parameters. So there would be a lot of things to say. You can do physics scaling ideas to think about where you have this cut for classification, and it has to do with the fact that it's actually a critical point. So your predictor, your function f diverges there, which is bad. And another regime that's really interesting is a fully over-parameterized one, where you take n, the number of parameters, to be infinite. And there were very interesting results with respect to that, but I think we will hear more about it this afternoon. And so the one key aspect is that when you take the number of parameters to infinite, deep learning is not doing something crazy, it's converging to well-defined algorithms. And they have a given, you know, predicted performance. And so there are two regimes that will be interesting here. And that depends on this margin. That's why it was here on this diagram. So, imagine you have a very large number of parameters. If the margin was very small, okay. What's understood now, I mean, the references are there, is that you enter a regime because the margin is so small, the function can change just a little bit to fit the data. And so you enter a regime where, yes, the weight, it's called the lazy regime, the weights do very tiny changes. And because they do very tiny changes here, you can actually linearize your predictor. And now your machine is just a linear function of the weights. Now, these are called kernel methods. Those were the methods that were the most popular before deep learning. So it's like we're backward in time here. So you have, for the specialists, you have kernels with, which are essentially linearized version of deep nets. And it's a bit easier to understand than deep learning, but still it's a question, what are those kernels if you have, you know, CNN architectures and so on. And now you have another, and so in this regime, very important, in this regime, you don't learn features. The weights are changing by epsilon. So what neurons respond to is essentially what they responded to at initialization before you train. So you have this regime where you're actually not building a nice representation of the data. And if you take a margin that's instead large, so this is dying, but yes, I don't know if one of you has another one that would work, but okay, so if you are instead in this regime, the weights change a lot, and there you actually build the neurons learn to respond to different aspects of the data. So one question I want to discuss is think about CNNs. So there are deep nets, not fully connected, where neurons know about locality of space. because they are the, the most efficient network. And I want to think, what are those kind of architecture good at in both regimes, when you're lazy or instead when you learn features? Okay, so to think about that, that's where we need to think about the structure. Well, yeah, learnability. What in the structure of the data make them learnable? And here are some ideas in the field, among others. Oh, thank you. Thank you very much. So, so those are ideas we like. Okay, for physicists, that would be rather, so we think that locality is very important. And I think those 3 points are presented for images, but if you think about text, I think they are also relevant. So locality is the idea that pixels that are nearby make sense together. Yes?
But just to understand better, in the previous slide, do you have a certain type of learning dynamics like formal regularization, or just what is underlying?
So those data were done in the purest. So we build algorithm where we try to track even gradient flow. So it's full batch. We do minimal, so we study the fact that we really try to, because we want to theory and we put no regularization. What we studied in those first work is that if you have regularization, for example, early stopping, as about the discussion in the previous talk, you don't go into the end of learning. Any regularization can kill this hump. It's very brittle. And that's because you kill the fact that the function overshoots. So this is related to the question of Giulio. So here you would have immense overfitting at the end of training. So actually you should, in this regime, that's where early stopping is the most efficient. We have a paper. But this second descent will stay even if you regularize. And it has to do, okay, that's what we worked out in those papers with Clément and so on. It has to do with the fact that those algorithms at infinite n, if you're at finite n, they start to have finite size effects. And you remember the initial condition, and it's bad. And with that, you can compute the sort of scaling, how fast you asymptote to the n equal infinity performance. Okay. So we think that locality is important. Another aspect is, that's what I want to talk about a lot today, is the combinatorial or hierarchical nature of data. So you know the fact that the dog is made of limbs, body, head. The head itself is made of ears, eyes, mouth, nose, and the eyes is made of edges and maybe a circle or something like this. And another aspect which I think is important is the fact that the task is sparse. I think it's supported by the fact that artists can, look at a picture and with a few lines, they make us understand what's on the image. So I think information is condensed in a few locations in the data. So those ideas are around. But they're very limited. Maybe so. Yes.
When you say sparse, you mean sparse in the real space basis, or because you could find the data which is sparse?
Yes, yeah, real space basis. And the way we think about it is the fact that people often that you have invariance coming from it. For example, if you are smoothly deforming an image, you don't care about the relative position between those regions with your information. So it means that you have made invariance if you start to move the image around, and that's what we studied empirically, stability to smooth transformation. But today I will not enter into it. I will just talk about this aspect. But thanks to interrupt me, because especially the second part of the talk, I would like it to be interrupted. It's a bit harder to present. Okay, so what we could do in those two papers was to think about the lazy regime, what CNNs are good. So CNNs are networks where, the first neurons are just looking at a small portion of the data. If you go deeper, the sort of receptive field of the neuron increases, but you really enforce locality in space, and you have a sort of, by construction, hierarchical aspect of the architecture. And so what we asked is, okay, if you're lazy, because that's a much more tractable, if you're lazy, what can lazy deep CNNs do? And we think that we sort of can characterize that. And a way to present the result is to think about regression now. So you're trying to really fit a function. And we play with the locality of this function. So we think about this function as being a sum of functions that are local. So they only depend on patches. So your data was in dimension D, but you assume that the function is a sum of functions that depends only on variables in dimension S. Okay? So S describes how local the task is. And now you can actually, using physics methods applied for kernels, you have to, what was sort of new in those work is to diagonalize the kernel for the specialist for CNNs. But what you can find is if your function is something like that, how many data do you need for the sample complexity? I call it P star. How many data do you need to learn that if you're lazy? If you have the usual architecture, which is fully connected, or if you have a CNN. And what you find is that for fully connected, if you're lazy, you're cursed by dimensionality. So even if xi is dimension 1, I mean S is 1, the number of data you need is exponential in the dimension. Whereas it's very different for a lazy CNN. So a lazy CNN is not cursed. It doesn't need a number of data which is exponential in the dimension. It just needs a number of data which is exponential in S. Okay. So, I mean, here we see that the fact that we have local filters immensely help if the function that you're trying to learn is itself local, or sum of local functions. But in some sense, those results are also a negative result because, I mean, CNNs in their lazy regime do okay for real data. I mean, but in the feature, I should have said that, in the feature learning regime, they do much better. Okay. And we think that, yeah, it's a sort of negative result because clearly when you're trying to recognize a dog, there is, long range dependencies between different regions of the image that determine that you are a dog, right? So, and as soon as you have that, being a lazy CNN is bad. So now we want to think about the much more difficult question of feature learning. And we cannot think about it in full generality, so we're going to look at special models. And what we really want to think about is how helpful it is if the data have some hierarchical properties. And we'll be thinking about, at the end, mathematically hierarchical compositional data, where the function of many variables will be a nested composition. So for example, that's a simple example with 4. You can iterate that more and more. That's what I'm going to do. But you had a function of 4 variables, but really it's a function. It's in fact a function of 2 variables. And it's a function of 2 variables acting on subfunction, acting on those 2 variables. And so these kind of problems have been studied. And I think the 2 most directly connected results to us is the fact that if you have deep nets, you can much more efficiently represent such functions. So it's something about approximation. If you have a finite width, how well do you approximate? So it's not about training with gradient descent at all, but those results are saying that it's much easier to represent those functions with a deep net. And there are other class of results that are more connected to what we do, where these good authors introduce generative models of hierarchical data, and I'm going to use them as well. And they analyze those models not with deep learning, but with special algorithm where you do a sequence of one-step learning with a shadow network and then clustering, and then you repeat again and again. And an interesting result that they find, which I think is completely correct, is that they find that actually the correlations between local region of the input and the output are very important to learn. And we'll confirm that. So really what we want to do in our case is really to study the real thing, gradient descent with CNNs. And what we want to answer, and we can't do it rigorously, but we have guesses that we can compare with observation, is how many data do you need to learn a task of a given combinatorial nature? So that's the game we're going to play. I will introduce those generative models in the next slide, and the one we like. But essentially, we're going to use them to generate labeled data, X, Y, according to some frozen rules. So there will be rules, and then you can apply an algorithm that generates data. It will turn out that the task will have a hierarchical structure of the kind I introduced earlier. So it's a bit less general because those function G1 will be the same, and G2 will be the same, but it's quite natural. It just means, for example, that if you're trying to build an eye from edges, it just has to do with translational invariance of the image, like an eye would be composed of the same thing on the left and the right of the image. That implies that those functions are the same. And then, once we generate those data, we study how CNNs learn those tasks in a supervised learning way. Okay, so here are the parameters that will play an important role. So NC will be the number of classes we have: cats, dogs, planes. And I told you there is this hierarchical sort of organization of the data. L would be what is the depth of this, how hierarchical that is. How many compositions do you have? Another quantity that will be important, so the dog, for example, will be decomposed into different features. And in this model, we're going to assume that it's always the same number of features, S. So here, for example, it was 2, but we vary this number. Another aspect of data that we want to capture is the fact that that sub-features can be shared. So, for example, a cat or a dog could have similar paws or edges or eyes. Okay, so you have shared vocabulary, so it's a combinatorial aspect of the data. And also an important aspect is the fact that that you don't have a single dog. You have, every time we'll take a decision, we'll have different ways to, from a high-level feature, decompose it into strings of low-lying features. And this degeneracy in this model is the parameter M. Okay, so let me try to explain how they work. How do you actually generate data? So the first thing you do is you randomly choose uniformly among NC possible choices, you choose a class. Okay, maybe this gray square goes for a dog. And then at the next iteration, you have a table that tells you, the dog, it has those 3 ways can be decomposed into 3 different ways, and the cat into 3 different ways, and the plane into 3 ways. So you have M possible for this dog, you look at this table, and you have M possible strings that encode it. And you're just going to choose one randomly, okay? And in fact, those function G's I introduced, for example, GL is just a function that goes from those strings to element of the class. So in this example, my parameters would be M equal 3, S equal 2, and V equal 3. So those rules are frozen. So each time I will generate a data, it's with the same set of rules. Okay, so at this level, I have M, so in this case, 3 different possible dogs, but then I can just iterate. And I have other rules that tell me, how the V possible features at this level are decomposed. This will be associated to this function Gn-1 I introduced. So you can just repeat this process. So, at this level, I don't have 3 dogs, I have 3 times 3 times 3, I have 27 possible dogs. Just a quick comment, this number, so I have so I'm looking at strings. Each element can be V elements, so there are V for S strings, but I have V objects, so that's the vocabulary at each level. For simplicity, I'm assuming that it's the same at every level. So the fact that I want that the dog and the cat cannot be confused, the strings do not overlap, so M has to be smaller than V for S minus 1. Okay, so in a model like that, the dimension of the input, so at the end, I started from a label Y, I ended up with a data X, and the dimension is just S for L. I have to tell you, how do I make a mathematical vector? At the end, once I have all those features, I just use a one-hot encoding. So just like colors in an image, each of those guys are encoded by a vector of dimension V with zeros except for one somewhere. And you can look at the number of possible data that you generate just combinatorially, and it's proportional to the number of classes times M, essentially for S for L. Okay, so it's exponential in the dimension, the number of data you generate in such models. So now I need to tell you, how do we actually specify the rules? You know, at any level of the hierarchy, I have to tell you how features are decomposed into strings of subfeatures. So how do I choose the strings? And here, to have something that we can track, we make the most simple assumption that those are chosen completely randomly. So for example, in the case where I had those 9 strings to associate, I mean, this guy, I just took randomly 3 out of those 9 and associated to it. I do the same for the second and for the third, okay? So I use purely random rules. My frozen rules are themselves random. Okay. Other question at that stage? I mean, the first time you hear about this generative model, it's not very easy. Yes?
Is it a random permutation of the possible rules, or is it you randomly draw the rules with repeats possible?
So once I choose the rule, it's forever, right?
Yeah.
It's completely defined a generative model.
Would purple have subfeature rules that are the same as gray's subfeature rules?
No, so they can, otherwise it will mean that a cat and a dog will lead exactly to the same picture from the start. And so you forbid that. No, so those sets are excluding each other. Otherwise you would, yeah. So in our model, a cat can never be misgiven for a dog. Other questions? Okay, so a point that will be key in what follows is that the fact that you choose random rules will lead to some correlation between subfeatures and features. So for example, if you look at the left pixel and you see that it's blue, it will mean that you know that your feature was probably gray. If it's orange, it was probably purple. So you start to have correlation between low-lying features and subfeatures. That's at one level, but they will propagate. So at the end of the day, we would have correlation between even the label and local region of the input. And those correlations will be very important. Okay, so what are the key properties of, so we call it the random hierarchical model because we took random rules to generate data. So here are the 2 key aspects of this model is the fact that you have synonyms, right? So all the 3 guys encode means the same thing. Just like for text, you would have synonyms. So you have this in this model. And so what it means is, for example, if you are generating a dog, but the gray feature here can be represented by those 2 strings. I mean, those 2 strings, if those 2 are synonyms, then it has to be the same class. Okay. And the second point, so let me say it again because it's important, is the fact that those random rules would create correlation between, for example, any pixel. So if you look at the left pixel, okay, I'm generating 1D vectors. I could have generated 2D images. It would just be completely the same discussion. So, but if I look at any position, I will have correlation between that position and the label. Okay. Okay, so now what we're going to do is just study those models empirically and then seek to rationalize a simple argument what we see. So what I told you is that those models can generate a number of data, a maximum number of data, which is exponential indeed. But now you can ask, if I have a given architecture, how many data does it need to actually learn the task? Is it polynomial indeed? Then you're safe, you beat this curse of dimensionality, or is it exponential in the dimension? And the first result is that, so here we're looking at the case where it's very degenerate, so I'm generating all possible data. So M is maximum in some sense. What you find is that if you try to learn hierarchical model of that kind with a shallow network, something that has say one hidden layer, it can fit anything, but it does very poorly. I mean, that's what's shown here. So this is for a one hidden layer, you vary the parameters, and you always find that the number of data you need to satisfy a given accuracy, your 70%, is just proportional to P max. So it's exponential in the dimension. So one, if you're not deep, you're cursed, you're doomed. You learn by heart. You almost see all data before you can learn anything. And in fact, we observe the same if you're a deep CNN but lazy. So in this lazy regime, you can't at all learn those kind of tasks. Yeah.
Actually, shallow fully connected net that you use is a fixed depth.
So we always try to scale the depth, the width, to always be in a regime where it's over parameterized. So we never want to have data to have measurements. So we study this over parameterized regime. So in this phase diagram I told you about, we want to know what happens when you have many parameters.
But you could think that when you increase D, you have to take the deeper length.
Yes, okay. So here when you increase L, you need to have a deeper length. Yes, it's L, sorry. It's L. I know it's I'm sorry for having 5 parameters on it. Yes, exactly. So here I want to say that if you're shallow, so it's one hidden layer, you're cursed. Okay? If you're deep, and then I will answer. I know the answer to this question, but maybe I tell it to you at the end. You ask the question again. Yes, we study. No, okay, here to go faster, we do SGD actually. We use hinge loss, I believe. We do SGD with the hinge loss, yes. In this case, we try to go faster to acquire more data. So we don't pay attention here to be close to gradient flow. So, but when we find that this result is robust when we vary parameters. I mean, I think it's very natural to that. And when you're lazy, you can yeah. I mean, so in those cases, you just can't learn. But if you learn that with a CNN that's deep enough, so the number of hidden layers needs to be at least going like L. And I can take the question on a fully connected net later on. Okay, so you found a bunch of curves. That's the test accuracy. So again, so this is the test error. Okay, so this is how well you do. You would like this quantity to be as small as possible. So when you don't have, and this is the size of the training set. So when you don't have data, you do poorly. And then at some point the test error drops, and again you can measure where it drops. And so when you vary all possible parameters in your model, it's actually a very simple result at the end. You find that the number of data you need for a CNN that learns features is just proportional to the number of class times M, how degenerate M was, how degenerate you are each time you take a decision. To the power L. L was the depth of the hierarchy. And it's actually independent of V, the size of the vocabulary, how many different features exist at different levels. And so what you find is that, yes, you have beaten the curse of dimensionality. You have a problem which is now, this is exponential in L, but the dimension was exponential in L, so it's just polynomial in the dimension. So just for, sorry if it's hard to track all those parameters, but briefly stated, if you're shallow or if you're lazy, you need to learn by heart. If you're a CNN that's deep enough, you do well. Okay, that's what you need to remember at that stage. So now so that's the central result in some sense. That's telling us what is the sample complexity as a function of the combinatorial and hierarchical nature of the data. It does not depend on V, depends on the power of L, and what matters is how degenerate each representation. Okay, let's try to think now. Let's try to have a simple argument for why is it like that. And so think about it. How can you actually learn this generative model? And again, it has to do with this curse of dimensionality. And the idea is that if you manage to learn, for example, from the input that this has the same meaning as that, those two guys encode for the same thing. Then you reduce the dimension of the problem. Instead of being S power L, it became S power L minus 1. So if you understand the structure of synonyms, that means a dog looking like that, or looking like that, or opening his mouth is the same thing. If you understand that, you lower the dimension of the problem. If you do manage to do it iteratively, then you can essentially kill the curse and learn. So is it actually what is going on? I mean, and then I will tell I can tell you it is what is going on, and then the question would be, how do you do that in practice? But empirically, you can actually study if your CNN, so this is a picture of the CNN we're using to train on those models, we can actually study with the representation that it has after training, if this is actually invariant to switch of synonyms. So for example, you have this input, we know that this guy means the same as this guy. We can just look at those two inputs and look at the representation and look at the norm distance between the representation when you do a synonymic change. And that's, okay, so I didn't define it mathematically, but it's essentially a L2 norm that you look at the level of representation here. And this plot is the important one. So what you see is here is P, the size of the training set you use, okay? And you look again after training and you look at invariance of the representation. In black, you have the test error. So where you have this inflection point, that's when you start to learn the task, this quantity I call P star. But in color, and you have two colors because we look at stability of the representation towards synonyms at different layers. But essentially, you find that, yes, that's a good intuition. Those networks learn the task precisely, so this sensitivity at initialization is down. It means when you go from here to here, the neurons are changing a lot their activity. But at the point where you learn, it's precisely the point where you also start to be invariant to those discrete changes that are synonyms. So it is actually the case that for those models, you learn precisely at the time point where you reduce the dimension of the problem and learn that synonyms just meant the same thing. And now I can give you, how much time do I have left? Oh, okay, good. So I went very fast. I went
That's including the question.
Oh, it includes the question. I'm good on time then. So now sorry?
So talking like 5 minutes.
Okay, I can do it. So now let me go through the simple argument. I should even call it a guess for what is this P star. And so what I'm going to, so what we observed is that many data you need to learn this kind of hierarchical combinatorial data is exactly the number of data you need to learn an invariant representation to synonyms. And that's what I want to think about. And so let's think a bit as a statistician. I mean, what's going to be special about, so I told you that those strings here, for example, this guy and these guys are synonyms, but they are, knowing them contains some information on the label. There are correlation between who you are here and the label, right? This correlation depends on the string you're considering, obviously. And so the correlation has a sort of given variance. Certain strings for given, say for the dog, certain string have a given correlation, others have a negative correlation, and so on. So those are those black lines. And what I call the signal is actually the variance of those correlations. But what's key is that if you are synonyms, you should have exactly the same correlation. In fact, more precisely, it's a conditional probability to have a class knowing who you are. That should be exactly the same. Okay, so if those two guys are synonyms, they should have exactly the same correlation with the output, with the label. Now, if you have a finite sample P, you don't have much data, you can't measure those correlations very precisely. You know, you're just from your data trying to measure those correlations. And so it will be noisy, and this noise will decrease as you increase the size of the training set. And so you can ask, when is it that the noise matches the signal? That's where this typical statistical game would start to be playable. And you find that when those two are equal, is precisely, give me the answer. It's P equal NC power ML. It's precisely the complexity, the sample complexity, our data I needed to have to learn the model. So this simple argument gives a good answer. We can go just a bit further than that and understand where this sort of statistical argument connects to gradient descent. And essentially, if you take a setup where you look at a one hidden layer, trying to learn those data, and you ask what happens in one step of gradient descent, you find that this one step of gradient descent is precisely sort of measuring those correlations. And so you do find in this setup that this characteristic P is indeed the number of data you need, such that the representation that you build in one step becomes invariant to change of synonyms. Okay? So that's where we have this simple argument that tells us, you know, that tells us when you should be able to start building invariant representation, and that gives us a good answer. Now, the full-fledged, you know, description of gradient descent in the deep net, I hope mathematicians in this crowd. I think this model, in general, it's going to be extremely difficult. Maybe in this model, I think in this model it's simpler because we know exactly what you should do. You should build synonyms, and so yes. So and we know the answer. So can we prove it and control more gradient flow? Okay, so we just conclude now. Okay, so if you're lazy, actually, CNNs, what can they do in the linear regime? Well, essentially, they are good at learning local functions, but they can't learn the hierarchical ones I told you about. And then we introduce this model. We call it the random hierarchical model. And it has a hierarchical task. And so we studied what happens when you do supervised learning with it. Another aspect on which we are very excited to think about such models are questions that will be discussed later on this afternoon. But this model, you have a hierarchical task, but you also have a non-trivial distribution of data, just P of X, itself hierarchical. And so you can think about self-supervised learning with transformers, you know, what ChatGPT would do on such models. Also, unsupervised learning, like Julie will tell us about later on. So we're working on those kind of problems. But here in this talk, what we find is that the CNNs, if they learn features, they can solve the sort of combinatorial task. And now we have a crude estimate of the sample complexity. I mean, well, if we know the hierarchical structure of the data in those simple models, we know what is the sample complexity, number of climbs, and the degeneracy for L. And okay, it's extremely crude. But if you look at data structure like Cypher and you look at the resolution, maybe you'd say, well, and maybe I would say it's around 3. How do I represent the face of a dog? Well, it could be in a few directions, opening the mouth, different species, okay. 10 classes. It's extremely crude, but at least maybe we start to have the order of magnitude or the order of magnitude of the number of data we need. And so it's also leading to a prediction, this kind of model that we're trying to test. It's in real data. It's a statement that you will start to do well at a task when actually you become invariant to synonyms. And so that's what we're trying to do. Look at images and change our orientation or opening the map of a dog. That's things you can do and test empirically. Okay, thanks for your attention. I'm done.
So, okay, maybe I can rephrase the question. So I have the impression that the function, hierarchical function is defined with G. So this, I mean, if you have, I mean, it seems at the first level of the hierarchy, since you're considering function of two variables, for example, so each function of two variables you can represent with one layer with the number that does depend on the dimension. So it looks like that if you have a hierarchy of order n, you can instantly a multi-layer perceptron with a number of parameter which is n divided by n number correctly. So
yeah. So I think that's a very simple point that I mean, it's a very simple point is that if you have a hierarchical structure like that, you cannot learn it when you're shallow. So it's sort of obvious. It's a sort of obvious explanation as to why depth is so helpful. Now there's a more quantitative question, which is here I'm using CNNs, which are actually know about locality of space a priori. What happens if you look at fully connected nets? And I can tell you, because we're also studying that. And so you find that it is the same dependence on M and NC, but you have you have another prefactor that's polynomial in the dimension. And what you find is that your fully connected nets learn locality. So neurons specialize, it's very complicated to treat mathematically, they specialize to look at only different patches of the image. And they do specialize even hierarchy. So they manage to do it, they pay a cost for it. So if you think about sample complexity as a polynomial in the dimension, the exponent is less favorable if you have a fully connected, but they can still do it. And that's another open question. How do you understand specialization of neurons and how they learn locality of space? But I think that's a nice model to think about that because we really control what happens. And it's a problem where you need that. A lot of the literature has to do with single index model where one hidden layer is doing all the job, but yes.
So what about using the attention mechanism in this context rather than CNN? Nobody uses CNN.
Yes, so
Okay.
I'm glad. So what we're very excited about, I think I like it, the fact that for CNNs, okay, so I would say it like that. At intuitive level, if you look at practitioners, that's how they think about it. I would build a hierarchical representation of the data. What I think was missing is the fact that, having a quantitative model to start thinking about that. But for transformers, ChatGPT, and so on, we don't even have the intuition of what's going on. I would say it's much more murky. And what I like about this model is that so it's most interesting in the case where you don't generate all data. Okay, so then P of X, the distribution of data is itself interesting and hierarchical. What it means in real space is that this pixel has strong correlation with its neighbors, but in fact, low correlation as you go along in space. I think that will also be true in text. If you have a word and the next one, it's more correlated. And so now we can play with self-supervised learning, right? Because we can ask, forget about this label, I'm not giving it to you, but I'm just giving you all those pixels. How much can you predict this guy? And then you can use, so that's what we're learning to train transformers to really ask this question in a very controlled setting like that, where you have this hierarchy of correlation. I think what will happen is that, correlation are stronger here. So you will start to understand the rules there, and then, but we don't know, we're just starting that. But I think this is maybe the most interesting aspect of those models that, here we're trying to quantify the intuition that people have, but we could try to go in ways where people even don't have their intuition yet. Yes?
So in this direction, am I wrong? Could we think of the structure of data as like having a teacher, which is convolutional and deep?
So the thing is that when you look at just at a teacher, okay, so I can tell you, we studied this at some point. That was our first model of hierarchical data. We said, let's just look at a CNN and assume that P of X is whatever, Gaussian or something. And then you generate, here's a task would be hierarchical. No way, this is the data. The data are what you put by hand from the start. So So you won't have the interesting data distribution, but you have the interesting task. Disappointingly, if you have a teacher which is a CNN, and we showed it in this first work, where was it? Here. If you take that as a teacher in the large width limit, okay, that's why we look at it. So maybe because we like this limit, okay, in the large width limit, then your output is a Gaussian field, and you can, its covariance is interesting because it knows about space and so on. But you can show with those arguments that the best thing to do to learn a Gaussian field is a kernel whose kernel is the covariance of the field, and this is cursed. So those models, taking this as a teacher is too complicated. Okay, so it's not a good model to think about how you can beat the curse. So that's why we think about generative model. Yeah.